The full ladder. A full ladder is a combinational circuit that adds two bits and a carry and outputs a sum bit and a carry bit. When we want to add two binary numbers, each having two or more bits, the LSBs can be added by using a half adder. The carry resulted from the addition of the LSBs is carried over to the next significant column and added to the two bits in that column. So, in the second and higher columns, the two data bits of that column and the carry bit generated from the addition in the previous column need to be added. So, this requirement is met by the full adder. Full adder adds the bits A and B and the carry from the previous column called the carry in or C in, and it produces an output as sum bit and the carry bit, which is called the C out. The variable S gives the value of the least significant bit of the sum. The variable C out gives the output carry. So, the figure shows the block diagram on the truth and the truth table of a full adder. So, from the truth table, we can identify the expression for sum S. The expression for the sum S can be obtained by checking the column S and identifying which all values are true. For each of the true value, obtain the corresponding combination of inputs. Similar is the case with carry. Identify which all values are true in the carry column, and for each of the true value, obtain the combination of inputs A, B and C in. So thus we can obtain the sum S is equal to A complement B complement C in plus A complement B C in complement plus A B complement C in complement plus A B C in, which can be easily written as A XOR B XOR C in. Similar is the case for C out. For C out, we obtain the expression as A complement B C in plus A B complement C in plus A B C in complement plus A B C in, which can be written as A B plus A XOR B into C in. The expression is represented by using the logic diagram. So here in the logic diagram, we can see that the logic diagram of a full adder can be used or implemented by using two half adders. Half subtractor. A half subtractor is a combination circuit that subtracts one bit from the other and produces the difference. It also has an output to specify if a 1 has been borrowed. It is used to subtract the lowest significant bit LSB of the subtrahend from the LSB of the minuend when one binary number is subtracted from the other. So a half subtractor, truth table, logic diagram, block diagram has been shown in the presentation. So we can say that half subtractor is a combination circuit with two inputs, A and B, and two outputs, D and B, where D indicates the difference and B is the output signal generated that informs the next stage that one has been borrowed. So we know that when a bit B is subtracted from another bit A, the difference between D and B borrow bit result according to the rules given as follows. The output borrow bit B is a 0 as long as A is greater than or equal to B. It is a 1 for A equal to 0 and B equal to 1. And from the truth table, we have obtained the value for the difference or the Boolean expression for the difference D equal to A B bar plus A bar B. And we know that A B bar plus A bar B is equal to A XOR B. So difference we can written as A XOR B. And then we have obtained the equation for the borrow B equal to A bar B. On the left side, we have shown the difference and borrow in terms of the combination of XOR and AND gate. Okay, the detailed representation is shown on the right side, where we have used two AND gates and one OR gate. The full subtractor. The half subtractor can be used only for the least significant bit subtraction, that is LSB subtraction. If there is a borrow during the subtraction of the LSBs, it affects the subtraction in the next higher column. The subtrahend bit is subtracted from the minuend bit, considering the borrow from that column used for the subtraction in the preceding column. Such a subtraction is performed by a full subtractor. So a full subtractor subtracts one bit B from another bit A when already there is a borrow BI from this column for the subtraction in the preceding column, and outputs the difference bit D and borrow bit B required from the next column. So a full subtractor is a combination circuit with three inputs A, B, Bi and two outputs D and B. The two outputs present the difference and output borrow. The ones and zeros for the output variables are determined from the subtraction of A minus B minus Bi. So this is the order of subtraction A minus B minus Bi. The truth table and the block diagram of a full subtractor is shown here. From the truth table, we have obtained the Boolean expression for the difference D, and which is equal to A bar B bar Bi plus A bar B Bi plus A B bar Bi plus AB Bi, which can be further reduced to A XOR B XOR Bi. And for the borrow B, for the borrow bit smaller the B, you have obtained the expression as A bar B bar Bi plus A bar B Bi bar plus A bar B Bi plus AB Bi. So this expression is obtained from the truth table where the borrow column, which all values are true, the corresponding combination of input has been taken, which can be further reduced as given in the figure as B is equal to A bar B plus A XOR B the whole bar into Bi. Binary parallel adder. A binary parallel adder is a circuit that adds two binary numbers in parallel form and produces the arithmetic sum of these two numbers in a parallel fashion. It consists of full adders connected in a chain, with the output carry from each full adder connected to the input carry of the next full adder in the chain. The figure shows the interconnection of four full adder circuits FAs to provide 4-bit parallel adder. The organ bits of A and addend bits of B are designated by the subscript numbers from right to left, with subscript 1 denoting the lower order bit. The carries are connected in a chain through the full adders. The input carry to the adder is Cin and the output carry is C4. The S output generates the required sum bits. When a 4-bit full adder circuit is enclosed within an IC package, it has 4 terminals for the organ bits, 4 terminals for the addend bits, 4 terminals for the sum bits, and 2 terminals for the input and output carries. An n-bit parallel adder requires n full adders. It can be constructed from 4-bit, 2-bit, and 1-bit full adder ICs by cascading several packages. The output carry from one package must be connected to the input carry of the one with the next higher order bits. The 4-bit full adder is a typical example of an MSI function. So next is the ripple carry adder. In parallel adder discussed above, the carry out of each stage is connected to the carry in of the next stage. The sum and carry out bits of any stage cannot be produced until some time after the carry in of that stage occurs. This is due to the propagation delay in the logic circuitry, which leads to a time delay in the addition process. The carry propagation delay for each full adder is a time between application of the carry in and the occurrence of the carry out. The parallel adder in which the carry out of each full adder is the carry in to the next most significant adder is called a ripple carry adder. The greater the number of bits that a ripple carry adder must add, the greater the time required for it to perform a valid addition.